This is what we've been waiting for.
This is what we've been waiting for. Taylor series. Okay. All right, so first we will look at a Taylor series that's centered at x equals 0, also known as Maclaurin series. Okay. So here's the formula.
Wait, are all Taylor series known as Maclaurin series?
No, only
Specifically
Maclaurin. So
Maclaurin.
Maclaurin are a subcategory of Taylor.
Okay.
So you got the big, they're all Taylor series, but Maclaurin are just for centered at x equals 0. Okay. So, and you'll see when we do the other ones, it'll say like instead of f of 0, it'll be f of a. And then we do f prime of 0 times x plus f double prime of 0, x squared, or over 2 factorial, and so on. Also factorial, we're good with. We talked about that before, like 5 factorial is 5 times 4 times 3 times 5. Technically, this would be over 1 factorial, and that would be 0 factorial, but 0 factorial is 1 and 1 factorial is 1. So, and then this is what it looks like if it's just a Taylor polynomial of order n. All right. So first we're going to learn to construct them, and then I'm going to show you some formulas that eventually you'll memorize. And if you don't memorize them, it's fine. It's just it takes you forever to construct them. So let's start with the first one. F of x equals natural log of 1 plus x. So first thing we're going to do, we want f of 0 is what?
1 or 0.
It's 0, yeah.
1 or 0. It's 0.
Fourth order means I have to go to the fourth derivative. Okay, so what's the first derivative? It's going to be 1 over 1 plus x, which implies f prime of 0 is 1. What's the second derivative?
Negative 1 plus x to the negative 2.
So negative 1 over 1 plus x squared, which implies the second derivative of 0 is
Negative 1.
negative 1. Third derivative. So that'll be 2 over 1 plus x cubed, which will imply the third derivative is
2.
And finally, the fourth derivative. So that's a negative 3 power, so it'll be negative 6 over 1 plus x to the fourth, which makes the fourth derivative equal to negative 6. Good? Okay, so let's put that all together with the formula. So the formula goes, we want f of 0 plus f prime of 0 times x. Now, keep in mind, this is a Taylor polynomial, so we will call this p sub 4 of x. Okay, well, the first one was just,
What question?
yeah.
So when it says the fourth order, does that not include that 0? It's 4 after that.
It's the fourth derivative.
So there's 5 things.
There's 5 terms. Now, in this case, the first term is just going to disappear anyway. So it'll be 0 plus 1x minus 1 times x squared over 2 factorial plus 2x cubed over 3 factorial minus 6x to the fourth over 4 factorial. which turns into what? Let's simplify that. So that'll be x minus x.
X squared. Or x squared everything.
Yeah, either way is fine. 3 factorial is 3 times 2 times 1. So what's going to happen?
X cubed over
The
3.
twos are going to cancel, so we get x cubed over 3. What about 4 factorial?
That becomes 24. The 2 and the 3.
The 2 and the 3. So minus x to the 4th over 4. So just constructing the 4th order, right? We can predict, so if we wanted to come up with the 7th order, we should be able to see that pattern. Good? All right, let's do. Yeah, so it's just going to alternate positive, negative, positive, negative. Yes.
What is this used for? Like, we get the series and then like, where do we?
Okay, so do you remember in the previous section we were doing like geometric series and so on, and we used it to approximate, like we talked about this. So basically a Taylor polynomial is used to approximate a function's value, in this case close to values at 0. Okay.
Oh, that's cool.
So what I try to do in this lesson is we just practice with it, and then I have a video that I'm going to show you next class that like does a much better job explaining than I do, but it gives you a visual. So it'll show like bridges and engineering and things like that, because you can take a Taylor polynomial. So take any function at all. Like we just did natural log of 1 plus x, right? So let's say I wanted to approximate this at a value that's close to 0. Say, what if it was f of 0.01? We can come up with any polynomial that'll evaluate that with very, very good approximation. So it'll take a natural log function and it'll turn it into a polynomial. And the idea is if you had an infinite series, it's actually equal to that function. So right now we're just going to take Taylor polynomials, and you'll see we're actually going to, where do we approximate them? I think we show more approximation in the next lesson. So we'll see like within what accuracy. It's actually like, again, this is how, if you think of, your calculators or computers, how do they compute things, right? So if you can turn anything into a polynomial, it's much easier to evaluate. You can evaluate a polynomial very easily, right? Okay.
Does this mean we're not going to have graphic calculator and do this on the test?
You're not going to have a graphing calculator for this part because I mean, listen, you can. Why? Come on, it's not hard. What's f of 0?
1.
1. Okay, what's f prime of x? 2e to the 2x, which makes f prime of 0 equal to 2. Then we get 4e to the 2x. I think we can pretty much go from here, right? What's the third derivative?
8.
And the fourth derivative.
16.
Okay. So again, what we're saying is e to the 2x is going to be approximated by a 4th order polynomial. We can even try this one if you want to see how close of an approximation it is. So what's the first term?
2x. 1 plus
Oh yeah, don't forget the 1. 1 plus 2x plus 4x squared over 2 factorial plus 8x to the third over 3 factorial plus 16x to the fourth okay. So what do we get? 1 plus 2x
Plus 2x squared.
plus 2x squared. This one doesn't work out as nicely because
Plus 4x cubed over 3.
4x cubed over 3 plus
2 over 2x to the fourth over 3.
2x to the fourth over 3. Okay. Yes.
Is there like a specific reason why the bottom's a factorial? Is that kind, or is that kind of just like the way the formula?
It's the way it's defined.
Okay.
Yeah. It's always going to be over factorials. Okay, good. How about a 7th order?
Oh no.
7th order for sine.
Wait, but we know that it's just going to be like sine, cosine.
It's going to alternate,
Yeah, negative sine.
and not only that, but every other term is going to be 0.
Yeah, that's true.
Okay, so 7th order doesn't necessarily tell us how many terms we're going to have.
Yeah.
So let's see. Well, we'll start out with f of 0, so sine of 0 is 0. Right, what's the derivative?
Cosine of it.
Cosine of x, which makes f prime
1.
1. Second derivative, negative sine. Third derivative is going to be negative cosine, which makes the next one
Negative.
negative 1. Okay, from here, can we just start going to, do we see the pattern? So let's go to the 4th derivative is going to be
0.
0. Do you see the pattern? 0, 1, 0, negative 1, 0. Okay, so 5th
1.
is going to be 1. 6th is going to be 0. 7th is negative 1. Okay, so putting that all together, we want again, what this is an approximation for sine. So P7 of x is going to be what?
Minus 7, or x to the 7th over 7. 0 plus.
0 plus x. I'll write it out first and then you'll see what, so minus 0x squared over 2 factorial plus x cubed, sorry, minus. This is plus. Minus x cubed over 3 factorial plus 0x to the fourth So what do we notice about all the even ones?
0.
All the even ones drop out. So we have x minus x cubed over 3 factorial. We'll leave it in factorial form because nothing's going to cancel. Plus 5x, or plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Blessing. So again, can you kind of see the pattern here? So if I needed to do more of them, what would the next term be? plus
Oh,
x
that's
to the
x
ninth over 9 factorial, so on. Okay, so those were all centered at 0. Now we want to look at what happens if they are centered around a different value. So this is Taylor series generated by f at x equals a. So notice here, we have to evaluate it f of a, f prime of a times x minus a, second derivative of a over 2 factorial. So it looks the same, just we're plugging in a, and then we have to do x minus a. Good? Okay. So we're going to do a Taylor series. We'll do e to the x evaluated at x equals 2. Now this is a series, so anytime it says series, we're going to have kind of like a dot, 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 and then we'll have like an nth term. Because this is an infinite series. Okay, I gave you an easy one. I just f of x is e to the x, so what would f of 2?
E squared.
E squared. Well, what would f prime of 2 be?
E squared.
E squared,
Yeah.
right? All of these are just going to be e squared.
How many terms do we have for this in a number?
I would probably just do like, I usually would recommend going to the third derivative. Okay. So the first term's going to be e squared plus e squared times x minus 2 plus e squared x minus 2 squared over 2 factorial. We'll do one more term, e squared x minus 2 to the third over 3 factorial. Okay, what would be our nth term? So remember how we're coming. So
x minus 2 to the n
e
over
squared
n factorial.
x minus 2 to the nth over n factorial. So now let's write it in summation form. So it's going to be e squared x minus 2 to the n over n factorial. Are we going to start with, are we starting with 1 or 0?
Oh, wait, no, you can't.
Oh, you
yeah,
can.
you can.
You
Zero
can,
factorial
you
is
can,
1.
yeah, you can.
Yeah, because the first term we want to just get e squared,
Yeah, so 0.
so we have to start with 0.
Wait, why is
Okay.
it 0 factorial?
That's a great question.
So if you think about the definition of factorial, if you think about the definition of a factorial, it's a permutation. It's the number of permutations. So how many ways can you put together 0 things? One way.
Okay, that makes sense.
Oh, okay.
Was that?
Yeah,
That's like the basics.
Yeah, that was a lot
That's like the
simpler than I thought.
basics, you know. It's like,
Basic number theory.
it's, how does that not make sense? How many ways can you put 0 things together? Just one.
I agree.
How can you put 0 things in order one way? No? That doesn't make sense? Kinda. All right, let's take a look at, okay, this one, I gave you all the derivatives, okay? We want to write a third order Taylor polynomial at x equals 1, and then we're going to use it to approximate f of 1.2. So remember when we did like linearization and all that, like to approximate? This is what Taylor polynomials are for. They're much more precise than a tangent line approximation. Okay, so let's start with the third order Taylor polynomial. So that's just going to be 3 minus 2. Now don't forget it's centered at 1, so we have to put x minus 1 and then plus 6x minus 1 squared over 2 factorial plus 2x minus 1 to the third over 3 factorial. You can. I wouldn't bother. If you want, you can, right? We would just make this a 3 in front of the x minus 1 squared, and that would make that just a 3 in the bottom. Okay, so now what I want to do, oops. So I want to approximate f of 1.2 by evaluating this. Okay, so that's going to be 3 minus 2 times 0.2. Now if you want to put it in there, maybe we'll write it 3 times 0.2 squared plus 0.2 to the third over 3. We plug that all in.
You got it, Augie.
You got it?
I could if you gave me 2 minutes.
If you gave, oh, you could do this.
No, it's not.
It would be easier if you wrote it in fraction form, if you wrote it as 1/5. So, right, 3 minus 2/5.
It's not that complex.
It's not that complex, but
You guys both have package, right? Oh.
it's fine. It's fine.
Worst cases, got it.
I have it written down.
Yeah.
As long as I did it properly.
In this case, so it's just the more terms you go, it would be more accurate.
Oh, yeah. And what's crazy is, like, when we're going to find out in the next lesson that all you really need are like 3 terms to get really precise. 4 terms will get even. You don't need a Taylor polynomial that goes to 10 terms. You'll find out that you really only need like 3 or 4 terms to get really precise. So that's why this is like very useful.
They work
and
for any function.
it works for any function.
What if the averages doesn't work, right?
Well, again, you're looking for values close to, like, we would not use this to approximate something at x equals 100.
Yeah. But
That wouldn't make sense.
if you go back to like the sine and cosine number,
This one?
that would diverge, right? So
What do you mean?
well, this one would,
No, the series?
yeah. So it keeps going back and forth between.
No, but it's not that
Well,
this,
because the denominator keeps growing, so
yeah, so here, let's look for a minute. These are the ones that I would like you to know. Now, if you don't memorize them, it's fine. It's just going to take you a while to generate it by hand, as long as you memorize that main formula. But hopefully these first ones we should already recognize because these are geometric, right?
Yes.
A geometric series also falls under a Maclaurin series, right? We should recognize that 1 over 1 minus x is 1 plus x squared. So that's going to, and then this is going to be true. Remember, the common ratio has to be less than 1, or the absolute value has to be less than 1. Okay, e to the x. This one turned out to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. This is true for all real numbers. Okay. Sine, we did. What did we notice about sine? It's alternating with odd exponents. Again, this is going to be true for all real values. Cosine, does the cosine one make sense? It's alternating but with the even, which would make sense if we were to go back and generate it by hand. And we also did this one. This was the very first one we did. Natural log of 1 plus x turns out to be the x minus x squared over 2.
E to the x.
What's wrong?
That must be a quiz 7.
Already?
Yeah, you already.
You just learned them. You're going to try to, you're going to recall them?
He couldn't do it.
Okay, so whatever you do, make flashcards, whatever, mark this page. I would memorize these specifically. It will make doing the homework, it will so much easier, the quiz, tests, because what we can do is once we know these, we can combine Taylor series, okay? So they can be added, subtracted, multiplied by constants, powers of x. They're also Taylor series. So what we're going to do in the next example, so we want to construct cosine of 2x using cosine of x. All right? So we'll do the first 3 non-zero terms, and then we want a general term of the Maclaurin series. And then we also want to give the interval of convergence. So that has to do with if it's geometric, right? It has to be less than 1, and then if it's and this one also between -1 and 1. The other ones are for all real numbers. Okay, so cosine of 2x. So
Would it just be minus 4x squared over 2, and then that's 16x over 6 over 4?
wait. Just, okay, you don't have to necessarily simplify these things, okay? In the beginning, I had you simplify because I wanted to show you a pattern. But what's going to happen here? Well, the first term is still just going to be 1. What's going to happen with the second term? So instead of x, I'm going to have 2x squared over 2 factorial, right? So I'm just looking right here. What's the next term going to be? Plus 2x to the 4th over 4 factorial.
Oh, wait, you don't have to take, not for every derivative, you just keep multiplying by 2, right? Wouldn't you keep multiplying it by 2? So like it would be negative sine, negative 2 sine.
That's what the power does.
Yeah.
That's the same thing.
Okay, I see, yeah.
Don't waste your time having to, again, if you construct it by hand, yeah, you would get 16.
Yeah, I just wrote 16 extra, but yeah, but like.
I mean, that's fine. You could do that. But what's my goal here? I want to end up with the nth term. Well, it's alternating, so I am going to have a -1 to a power, and then the rest of it is just 2x to the, well, they're even powers, so I'm going to say 2n over 2n factorial. And if I make, so if we start off with n equal to 0, this will work, right? It doesn't matter. You can make it, you could have it start at 0 or 1, right? And then this is going to keep going just to show, remember, these are series, so they're infinite. And this is true for all real x. Okay, how about e to the 4x? So,
1.
right, so the first term's still just going to be 1. Then the next one, so instead of plus x, it's going to be plus 4x. And then the next one's going to be, so,
Squared over.
Why for the other one, for the cosine one, why is it not plus 1? Isn't that, wait, never mind.
we're good?
Yeah.
4x squared over
2 factorial.
2 factorial. Okay, and then we keep going. And What's the general term? Question.
Remember when you do the derivatives, you just like plug in, right? So it becomes a constant. Like e squared is just a constant.
Yeah, so like if I were to do this by hand, right? Like if I did f of 0, that would just be 1. Well, f prime of x would be 4e to the 4x.
But they're all just zero.
But then
Yeah.
that would mean, yeah, so then f prime of 0 would just be 4.
Yeah. Like the e is not going anywhere. It's just that.
And then what would happen with f double prime? It would be 16, which is the 4x squared. So if I just make this, what, 4x to the n over n factorial, and this is true for all real x. Remember, what we're doing is we're taking this function e to the 4x and we're turning it into a Taylor series. And that Taylor series to a certain number of terms will be an excellent approximation for that original function. Okay. All right, last one. Well, what would 1 over 1 minus x squared be?
X squared.
Okay, look at our Maclaurin series. So I know if I take 1 over 1 minus x, but I replace the x with x squared, what would that be?
Plus x squared to the n. Right, there should be x.
I know, but let's write out the terms first. It will be 1
Then we also have an x.
plus x squared plus what? X to the 4th, and so on. So what would happen if I multiplied x to that? Right? Imagine if I factored out the x. So this was just 1 over.
I'll just get 1 power higher.
Yeah, so if I take this and I multiply it by x, I'll get this.
Is that bottom one supposed to be 1 over 1 minus x?
No.
No.
Here. What's 1 over 1 minus x?
1 plus x squared plus x to the third.
X to the 4th, dot, dot, dot. Now, what if I replaced all my x's here with an x squared? Squared. X squared squared would be 4th. This would be x to the 6th, x to the 8th, and so on. Now, what if I multiplied x times 1 over x? Right? Isn't that what, or sorry, that's supposed to be an x squared.
So it's just x
So
squared x.
isn't this the same thing as this? So what if I multiplied all of these by x? That's my, you see what I'm saying?
Yeah.
So we're taking the Maclaurin series because this would be a pain to do the derivative of, because I would have to do the quotient rule every single time. So imagine having to generate this by hand. It would be so much work. So if you can take one of the ones that we can, like, oh, there's a delay. So if I could take one that it looks like and kind of take it apart, then I can come up with a series much easier. So this one will be what? This will be x plus x cubed plus x to the 5th
X to the 2n plus 1.
Good. So just keep in mind all even powers we're going to express as 2n, odd powers 2n plus 1. And what is this going to be true for? Well, this has to be true for,
Absolute value of x is less than 1.
yeah, so for values between -1 and 1. And that